You are listening to the Lasker podcast series, We Ask a Scientist. In this new series, you will hear notable scientists discuss the roles of instinct, uncertainty, and inspiration on their road to success. They talk about their approaches to collaborations and how they handle roadblocks. As you listen, you will find that there is no one path or general principle to follow when doing biomedical research. Rather, there is freedom to question existing solutions and freedom to imagine new possibilities. John Jumper is a physicist, computer scientist, and, together with Demis Hassabis, a 2023 Lasker Laureate. He currently serves as a director at Google DeepMind, where, together with colleagues, he created AlphaFold, an AI model to predict protein structures from their amino acid sequence. He is also a Nobel laureate and Fellow of the Royal Society. John Jumper, welcome to the Lasker podcast series, We Ask a Scientist. Thank you for joining us. My first question for you today is, how did your path in science begin?
So both my parents are engineers. My father is a mechanical engineer. My mother is a civil engineer, and, very practical people. And they supported me in science, but they always were a little, what about engineering? What's really practical and impactful? But I kind of love these questions of the universe. And I started as a physicist, or loving physics, first of all, like even into high school. And then sure that I was going to be a physicist discovering the laws of the universe. And so that's kind of what I went to college, and I majored in physics and math, and I was going to discover the very equations of the universe was my goal. In fact, did physics and learned a tremendous amount. Then went to do a PhD in physics, and I didn't love what I was studying. It didn't quite grab me, so I dropped out of this PhD in physics, and I got a job, and I happened to get a job at this really interesting place that was trying to understand how proteins move and do simulations of proteins using big custom computers. And that's kind of how I got into biology.
Was there any particular person or event that oriented you and shaped your research project?
One of the things that was really important to me, I think there were two sets of things, right? I work in biology and I work in AI. And I think in terms of kind of biology, it was the people that I met at D. Shaw, where I worked, who were really talking about, how their work mattered to, patients with cancer, how this really worked. To me, that was this eye-opening moment that this science cannot just be far in the future, but can be really, really immediate. In terms of kind of AI, there was this book by David Mackay, who told basically the story of machine learning and AI, but told it in the language of physics, and kind of said that this physics that I knew and loved, called statistical mechanics, was really the same as AI if you kind of squint and rotate your head. And it was this incredible book. And then I started reading all these things, and it kind of made statistics jump alive for me, that it was no longer kind of this linear regression you did on your way to doing something else, but it was this, kind of living subject that told really cool stories about really big, impossible problems. Like I learned this method that, AI researchers developed, or they would consider, statistical researchers developed, called Lasso, which could take an enormous data set with many kind of information about each data point and only a few data points, and say something relevant about it. And to me, this was kind of magic. It was this moment at which these really, really cool tools of mathematics also told me, how do I think about the world? And it wasn't I was used to the kind of simulation view, but this was kind of what made the data view of the world jump out at me, that this was something that could say something important.
I have a question for you about uncertainty. Could you talk a little bit about the relationship between uncertainty and science?
Science and uncertainty are so very linked. And people imagine, I think, this kind of popular conception of scientists is a group of people certain and certain about many things. And maybe you could say that about mathematics, right? We have proofs, we have facts about which we're certain. Although even if you talk to working mathematicians, they have the facts about which they're certain and the facts that they believe, and the facts that they believe are much more than the ones they're certain about. Even more so in science, that science is about developing evidence for theories, right? So we only work on things we are uncertain about. And in fact, science is very rarely resolved in a single paper or a single experiment. We go back and we tell that story that there was uncertainty, and then a brilliant scientist did an experiment, and then there was no uncertainty. That does happen occasionally, but that's not the normal progress of things. It's really we're working at the edge of knowledge. We're working often where it's very, very expensive to investigate things. It's very common in biology for a single paper's set of experiments to take more than a year. Sometimes it takes more than a year where you wait for your sample to be ready. And so we're almost always operating with far less information than we need and a set of beliefs, and then we try and solidify that. We have some things that we've solidified really well, and we have quite a few things that people will say they believe, but not completely. And that's the things we work on. We try and work on the things that we don't understand. And scientists have to be a rather optimistic bunch in the sense that you're kind of I think I once saw a joke that a grad student is someone who bangs their head against a brick wall, believing the wall will give first, right? But but we're always working in the face of this uncertainty to gather enough evidence that we've pushed this discussion forward. And I think the discussions happen across the community.
I wanted to ask you a question about collaborations. How does that work for you with regards to negotiating priorities?
So, Google DeepMind, where I work, is a really interesting, is a special place. We tend to work on relatively large teams. The AlphaFold team was around 15. And when you have 15 people who are really, really working shoulder to shoulder on the same problem, talking to each other daily, you have to have an organizing principle, right? And I think it's not just like you can say, oh, well, we'll try and do good things. You really have to be behind a principle. And for us, it was, this problem of predicting protein structure is important. And in fact, we'll say that, you can you can use data from this time period, say before April 2018 was what we used for a lot of the project. And then you can only check your performance on data afterwards. And we will all agree that we, like whatever is best according to that. So we tried to say, we don't know how to solve this problem at this moment. If we knew how to solve this problem, the science would be over. And so but what we can agree is how to measure progress, and that we are going to try and get even small gains in progress, right? It became very clear pretty early on that, we weren't just one idea was going to jump us from doing nothing to doing everything, that we were going to grind through many small to medium ideas that would actually be progress. And so we kind of oriented ourselves around this. And so we would have many, many people trying whatever idea they think is best, and lots of discussion and lots of just kind of sitting around and guessing and developing our own personal theories of why something works or doesn't work. But at the end, we would measure, and we would measure really well. And that was kind of our organizing principle. That's how we kind of ran as a collaboration and as a team.
I wonder if you could talk a little bit more about communication within the team, and also what makes you a good communicator, and how did you learn?
Am I a good communicator? Um, I think there's a couple important things in really communicating, certainly within a team. One is to make sure that everyone kind of understands where we want to go, that or what does progress look like? Because you want people to be autonomous agents. You want them to be able to say, well, I know this is a group priority and I'm going to do this. And, when I succeed, people will like it. And so everyone has to know why we're doing this. And they have to know kind of, because it's research, because we don't know what's going to work, they often need to know not just like the sub goal of, write a piece of computer code that does this, but they need to know I'm writing a piece of computer code that does this because we think this piece of data will be important to training our AI model. And so I think part of communicating is really kind of getting everyone in a room and having everyone talk and everyone say what they're working on, everyone say, and kind of gardening this into we're going in this direction. And so I think that part of the communication is just being open with people and assuming they're senior enough to know why we're doing this, telling them not what you want them to do, but what the team needs achieving and where you think they might fit into that. I think there's another aspect of kind of communication of making sure you celebrate the things that are good and that you celebrate everyone's achievements in all the areas you communicate that the whole group's work is important. Each person's work is important individually.
And if conflict arises, how do you deal with that?
On conflict, I've seen a couple of types. I think the best kind of conflict is the one that can simply be resolved objectively. So one type of conflict that shows up all the time in research teams is, I think we should do approach A, and someone else says, that'll never work, we should do approach B. And normally what I've found is that, I can normally talk to people and say, okay, if you're right, if approach A is correct, but approach A is going to take you 2 months and 5 people to figure out if it works. What's the simplest version of this idea? What's the dumbest thing that you can do in 4 days? And I've never gotten anyone ever to give up an idea they really love and believe in, but I've gotten them to shrink it down into an experiment that they can do. I can say, that's great, but you have until next Tuesday to figure out if this is a good idea. And almost always they'll come up and say, well, I could make this one line change. It's not exactly what I want. And then if it's good, then we all agree maybe A is a good idea and we should invest more in it. And if it doesn't work, they will have convinced themselves that it's not a great idea. So I think like having an objective metric and then encouraging people to kind of simplify their ideas, to do the grandest thing, to make the short film instead of the feature film version of the idea, that helps a lot. I work with really great people. We haven't had that much interpersonal conflict, although almost always, I think the other important thing is to realize that if you work with good people who are normally quite reasonable, that interpersonal conflict is a sign of something underlying, and you should figure out what that is. And you should, watch for these problems as they grow, or watch for the person that seems unhappy with a decision and engage them on the side. And I think it's also trying to make sure that everyone feels kind of respected and participants in the community of researchers that a team is.
I'd love to hear your thoughts on instinct or intuition. Does that play a role in your research process?
It's absolutely everything. People have this assumption that scientists, derive things, and very rarely do scientists derive things, really, especially in biology. Even more than that, nothing is fully ever proven, right? So we say that, someone did an experiment and, it is true that disease X is caused by Y, but that's not really the experiment they did. They really did some sort of intervention where they knocked out this gene and measured the expression of that gene in some way and then concluded this other thing. So I think part of it is always there's an intuition on how you go from kind of minor bits of information that you collect from an experiment, whether computational or a wet lab experiment, out to what you now believe about the world. And I found that some of the best researchers will make conclusions on what looks to everyone else, often including me, as no evidence at all. They will say, oh, look, you know, the model got 4% worse when I removed this piece, therefore it's useless. And a bunch of other people will say, well, how do you know you can get that 4% back? Or that this is a good change. And they will believe that it will be almost hard to argue with them. They're like, no, 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 look, it's clearly proven. And those people are kind of, their intuition is interacting with their small amount of data. And the very best people are normally right. When they're sure, they're normally correct. Now you get them to do the experiments to continue and improve it. But I think all of this is about intuition. And even within the project, we developed all these kind of mini intuitions on like extraordinarily technical matters of, oh, you can't use a one-dimensional representation in this part of the pipeline or the results will be terrible. And it's because we tried 4 versions of this and it didn't work, and we're concluded that, this whole idea is busted. And all of these kind of mini intuitions shape what you choose to do next. Because as a scientist, you're ultimately trying to allocate your own time. You have uncertainty, you're kind of, in a sense, starting a business where the business is the next experiment you do, and it's going to require an outlay of your most precious resource, your time, and your second most precious resource, your compute. And so always intuition guides those. And also working in AI is incredibly kind of failure heavy field day to day. I like to say that someone who 9 out of 10 of their ideas don't work out is probably the most successful AI researcher I know, right? That the failure rates are just absolutely enormous. And we make up for it in testing ideas quickly and moving on to the next one and rolling that into our intuition and our choice of the next thing we do.
In a somewhat adjacent question, I wonder if you could share your thoughts on the role of creativity in your research process.
I think that kind of, especially in AI research, where none of us believe that we're discovering the only way to solve these problems. We believe we have an instance of a way to do an AI system which predicts protein structure. And we believe there are many other instances of ways to do it. And I think it's kind of liberating is that what I love about AI research is you get to be incredibly creative. You kind of draw the ideas you want, but then it's grounded. The creativity is in service of this objective of understanding the world better. And so it feels very creative. You sit around, you think, you talk, sitting on the couch and talking can be the most productive use of your time, and kind of sharing in this creative process. And at the end, it's not unlimited creativity, right? You're not just trying to create something aesthetic, you're trying to be creative because it will improve our understanding of the world. And I think getting that kind of tight feedback cycle is really wonderful to me. I don't, like necessarily creativity with purely aesthetic goals. I like this creativity in the search of something cool and simple. And when you create something and it works, you have an unbearable urge to tell everyone about it. And I think sharing in that kind of, and there's nothing more fun than saying, well, we were going to do it this complicated way, but I was very clever, and you can change this number to a 5, and for this reason everything works. And I think that kind of creativity is probably the most rewarding kind of day-to-day moment of the job.
On the subject of public trust in science and medicine, how do you think that can be improved?
So I'm no expert, I should say, but part of this, I think, is better communicating to people what the process of science is. And I think part of it is also communicating kind of how the scientific conversation occurs. Too much of the time, people say, scientists published a paper that shows this. And then a year later, scientists publish a paper that shows the opposite of this. And they say, well, how can you say science said X and then science said not X? And they're absolutely right. Because you ask kind of working scientists, like, I don't know any working scientist that says, this statement appeared in a peer-reviewed paper, therefore it is true. Don't know a single one. Peer review, is a check, it improves quality, but it doesn't, it simply certifies that this paper is a worthy contributor to the scientific discussion. And I think so part of improving, this is to really help people distinguish between the edge of science where no one is sure and the core of science where people are much more sure. And the tendency to kind of overstate things in our science communication really harms that. And it's really, really hard for people to understand that papers are not definitive and all of them are read by working scientists with deep, deep skepticism. They often find them valuable and the experiments valuable, but very few people take the conclusions at face value, and certainly not the experts in the field. And I think that's hard to communicate. I think it's one that we could do a lot better job of and do a lot less of saying science says X. That expresses a certainty that's never true at the edge of science. And we see events like kind of the discussion around, COVID and COVID policy and what did science show as a really challenging instance where people wanted science to create certainty at that moment. And science wasn't ready to do it. It created a lot of conversation. But I think that harms public trust. It's hard when you say scientists say X and it may get reversed later. But it's so tempting in the moment to say, and scientists believe my paper shows X. And it's hard to fight, but I think it's one that really bringing people into the process on the uncertainty of science is really important.
This is a question about the future of biomedical science outside of your area of expertise. How do you see that future, and how do you see it affecting your field?
So, one of the really, two of the really interesting questions to me in biomedical science. Like, biomedical science is extraordinarily difficult because we have far less control over what we study, right? We want to talk about, people, but we have to be extraordinarily, safe and responsible as we experiment on people. We can work on individual cells, but then, how do they don't function often individually, human cells. They're, meant to be part of a system. And, how do we measure this? How do we collect data? How do we collect the kind of data that will let us make useful predictions? So I guess one aspect of the future for me is as we learn to build, better manipulate cell systems, tissue systems, organoids, hopefully we can get better transfer from what we can do easily, right? The experiments we can do easily, and the ones that are more directly related to human disease. And I think this kind of yawning gap between the systems that people experiment on, including, mice, and what the data we really want, which is what will this do in people. I think that's a big, big area that people are closing better and better, and they're learning to manipulate cells better, learning to build better synthetic systems. And I think, one of the things really that it will impact is as we get more and more data on more complicated systems, and as we can do it at scale, then the people who work with data in AI have something to work on, right? We can talk about this large gap between, say, a simulation view where you simply understand the smallest elements and then propagate that understanding outward to the largest things. Well, that's hard to do at the scale of a human, right? We really need more data at more scales. We need it to be very closely related to humans. So I think that will matter. I think also reproducibility is really, really hard in things like animals, even in often cell lines. Heard a really incredible story from one researcher about a certain pituitary phenotype they were looking at, and they couldn't reproduce their own work after they moved their lab, and it turned out to be the gut microbiome of the mouse. That only with a fecal transplant could they even reproduce their results for something in the brain. And I think this kind of complexity, we have to control it in some ways to get durable scientific facts.
I just have one more question for you. Could you describe what you see as the future of AI in science?
I really like to think of AI as an amplifier of experiment, as a way that you can get a couple examples and then you can generalize to many. You can turn, instances into a type of, somewhat trustworthy oracle that you can ask questions and get answers. So to me, I love this notion that we'll be able to collect some pieces of data. So I work in proteins, and so protein data was aggregated, and then we can turn that into a general tool that can answer the same kinds of questions, but across many, many proteins. And this will matter a lot. So part of it will be this amplification. I think what remains to be seen is what will things like language models or things that work directly, say, on scientific papers, what will they mean for science? And I could imagine futures in which they're extraordinarily powerful in their understanding of science. They're operating at the kind of understanding of scientific text. And I can imagine some where they're very useful. They help us do literature search. They help us organize things, but maybe they're less good or useful at the science itself. So I think that, to me personally, is an area I'm very interested in.
Thank you for joining us for this episode of We Ask a Scientist. Please visit laskerfoundation.org to learn about our mission and programs, and for access to all our podcasts. We sign off with Mary Lasker's famous words, "If you think research is expensive, try disease."